what we're looking at again this week, at least for the first two lectures, is going to be linear systems of equations. And we're getting to a scale now. We're doing some serious computation here, whether you have realized that or not. We're going to explore that more thoroughly today. The reason we're putting some stress on our computer CPUs now is because the scale of the calculation we're doing now is far beyond anything we would have done before this. The last system of equations we were looking at were the truss system. Trusses, 10, 100 joints, that kind of thing. When we look at this temperature distribution, we're taking a grid of points. We need an equation for every single grid point. So that's 5 by 5, means there's 25 equations, 5 squared. If we make it a 10 by 10 grid, that's 100 points. That's 100 equations we need to solve at the same time. And when we tried exploring like even a 50 by 50 grid, that's 2,500 equations to solve. This is getting big, and it's really easy to want to make larger systems because the more points we use, the more accurate our answers are going to be in terms of the temperature distribution. So, just a brief recap of the kinds of equations we ended up with for this actual example. The heat in and out of each of these little grid points, these little grid squares, was meant to be 0. We're talking about the steady state, so in the long run, what temperatures do we settle down to? Well, whatever temperatures we settle down to, the inflow and the outflow have to add up to 0, just like a balance of forces. And that led to a bunch of equations for these unknown temperatures. What we want to know is, hey, how hot is it in slot 4 over there? Well, we don't know, but we know it's in balance with its neighbors. And that led us to a series of equations that we derived last class. That led to a matrix form. So if we just isolated the unknown temperatures, so we had 25 unknown temperatures on this side, and their coefficients, some nice structure just started popping out at that point there. We ended up with this diagonal elements of these -3s and -4s that had a pattern. Does anyone remember why we had -3s in there? Just out of curiosity. Why were some of those -3s? Yeah. Corners? That wasn't the -3s. That was the other things. Yeah. Insulated side, exactly. So there's a few different factors at play, but it came back down to, it came back to the diagram and how these pieces are related. All the pieces along the left-hand edge were beside an insulated wall, so there's no heat transfer. So instead of having 4 neighbors, like the guys in the middle or the other side, there were only 3 neighbors. And so that 3 showed up in our coefficients. And the outside corners and things like that, they had to do with the B vector. These 20 and 120 are just numbers. They're not multiplying any of the temperatures we don't know. And so they ended up out here. All right. So there's lots of good reasons and very straightforward reasons for why these numbers are what they are if we want to keep the heat balance, the heat flow to be 0 in and out of each cell. Very straightforward calculations, but tedious. Once we start doing this in large scale, it gets a little cumbersome. In terms of the actual solving, fortunately, it was pretty easy. The top line there we started with was that we know A and we knew B, and this finds or solves for a vector of the final temperatures on the grid. T1, T2, T3, all the way down to T25. That's what that calculation did for us. It solved those 25 equations in the blink of an eye, actually, as it turns out. Okay. There's another command that we saw last class, which is the reshape. What did that guy do for us? Yeah, at the back. It converts it to a matrix, exactly. Remember, just going back one page, this T is going to be 25 numbers just in a big long list. So that's great, but it's not the way we're imagining it, because again, we go back to the picture. I'm imagining this as T1, 2, 3, 4, 5 in a row, then T6, 7, 8, 9, 10 in a row, but that's not the way I'm getting it back. It's fine. This is all the information's in this vector, but it's just not laid out the way we'd want to use it naturally. So this takes the column vector T1 down to T25 and turns it into a 5 by 5 matrix, which is T1, T2 to T5, and T6 to T10, and so forth, until we get down to T25 in the bottom here. So this is the grid layout where we started. It makes it much easier to interpret. All right. Now we're going to get into some minor variations here. So this is almost what we did last class, but there was a part of it I didn't explain, well, at all really, last time. So I want to explain that now. This stuff's all the kind of thing we displayed last time or went through last time. So we're going to run this. Function F5. Notice we get our temperature grid down here. Colder stuff at the top, hotter stuff at the bottom, because the bottom plate, bottom part of the plate was exposed to 120 degree temperatures. The top was only 20 degrees. And we end up with this grid here. Okay. So that what generates that grid is the pcolor command. So this generates the color plot. And the color bar command, if we take a quick look at the sidebar here, the color bar command is what adds this little vertical scale of what the colors mean in terms of temperatures. Oops. Adds the color scale. There we go. Alrighty. So let me just pause there for a second and ask if there's anything there. We're going to investigate a bit further, but anything there that's causing any concern or any problems running it from the file that was on the course website. Okay. Excellent. All right. So now we actually took a step back. This graph is not as good as the one we had on Friday last week. We're going to tweak it a bit and figure out how we can improve it. So let's take a step back here, back to notes. First off, as someone pointed out on Friday, we only have a 4 by 4 grid. Sorry, question, yes? That is an excellent point. The hottest part is up there in the corner, but we just said that the hottest part is down in the bottom right corner, not the top right corner. That is something we're going to have to fix. You're absolutely right. So that's one of the problems, and there's another one we're going to fix at the same or along the same time. Let's get into that. Sorry. First thing though is, why do we get a 4 by 4 set of blocks instead of a 5 by 5? So you had a 5 by 5 grid. Briefly mentioned this last class. Yeah.
Because like it averages around or something like that.
It averages around, exactly. So what we think of as a point here, MATLAB is also, or what we're thinking sort of as a little area. MATLAB just takes that as one point, because it's easier for it to imagine points than grids. And so at the point 1, 1 here, it put the temperature 38 degrees. And then at the point 1, 2, it put 39 degrees. And so it has 4 points, would be these 4 elements. I can't highlight them exactly. But these 4 elements in the corner here, those are the 4 numbers that lead and then average the color to get the distribution on that overall cell. So it's not quite what we want, but it's pretty close. It's pretty close. Okay. But what else is wrong with the plot? So as someone pointed out, this should be the hottest corner. But on our grid, the hottest point is up here. If we take a look at our plot, yeah, the 100 and whatever degrees is way up high. Why? Any thoughts? Yeah.
You encoded in your space for SY to 0.
Okay. Right. So last class we used a linspace and some mesh grid. We're going to derive that today. I wanted to get to the final answer last class. But well, what's the numbering scheme here? I'm going 1, 2, 3, 4, 5. Where's MATLAB getting those numbers from? Where do you think? Given that all it knows about, if we look at the command for pcolor, it's handed TM. That's all it knows about. So where do you think it's getting its 1, 2, 3, 4, 5 from? Yeah?
What element in the array?
Exactly. What element in the array? Rows and columns. All it knows is there's a matrix of 5 by 5, and it's got rows and columns. So what it's doing is plotting the first row at height 1. So at y equals 1, we're getting 5 numbers, and then it does the interpolation. And then at height 2, and then at height 3, 4, and 5, well, like we just said, we're imagining row 5 is the furthest down. But if we talk about y coordinates, y equals 5 is going to be the top because we go upwards when we talk y coordinates. So it's just one of those annoying mismatches between matrices and counting versus graphs and counting distances. Fortunately, in both cases, we count from left to right. If we talk about columns, 1, 2, 3, 4, 5, and we talk about x values, x 1, 2, 3, 4, 5, those both go left to right. So it's not like everything's flipped. It just tends to be the y values that are flipped, because we count a little bit differently on graphs, which go up, and rows, which go down. So if that makes at least a little bit of sense, now we can get into fixing this. The other problem is, this is actually supposed to be a 1 centimeter by a 1 centimeter plate. Way back in the dawn of this, we said that. So we also don't want to go from 1 to 5. We want to go from 0 to 1. That would be the ideal. So 2 minor tweaks to this graph. One is to put the hottest part of the plate where it should be, and also just to scale it so it behaves appropriately.